Okay, AP Environmental. Today we're going to be discussing topic 6.6 out of Unit 6, and this topic is on nuclear energy. So we've been talking a lot about how we, for example, generate electricity, using fossil fuels or using coal, natural gas. Today we're going to be talking about how we can generate energy from nuclear power. And basically, whenever we're referencing nuclear energy, we basically are talking about um, producing electricity from nuclear energy. So in the United States, for example, last time I checked, I believe like 10% of all the energy or of all the electricity in our country is produced using nuclear power. Not using coal. It's done using nuclear. So we get quite a bit of our electricity from that. Um, Now, the thing about producing electricity, I don't care where the or what the fuel source is. It doesn't matter if it's coal or natural gas or if it's nuclear fuel. The whole point of producing electricity is to produce enough heat to generate steam that will turn a turbine, right, and then produce the electricity. So really, kind of the overall goal is to again produce that electricity and get that turbine to spin. We just use a different fuel source when we use nuclear energy compared to if we were using a fossil fuel. Now, in nuclear energy, we use a radioactive isotope called uranium 235. Uranium 235 is a non renewable. It's something that needs to be mined for. So, I mean, there are some mining issues, as far as like pollution and that goes. But we have to acquire this particular fuel source, and we can use it again to help us produce electricity. Now, the thing about uranium 235 is because it's a radioactive isotope, this kind of takes us back to our chemistry days. It does undergo something called nuclear fission. Now, if you're not sure what nuclear fission is, this little animation here, I think, does a pretty good job of kind of showing you what it is. But it's basically when a neutron strikes a relatively large nucleus of an atom. And uranium 235 is a big nucleus. I mean, there are 235 protons and neutrons in the nucleus of a uranium 235 atom. So when a neutron hits that, it causes that nucleus to split. In fact, that's what fission is. Fission is the splitting of a nucleus. And once that occurs, you'll notice here, the neutron strikes it. It produces more particles that are free to strike other uranium 235 atoms. So we call that a chain reaction. And the more the reaction goes, the more energy is produced, the more heat is produced, and that heat can be used. It can be used to do work like, boil water to produce steam to eventually, spin a turbine. Here it says 1 gram of uranium, contains 2 to 3 million times the energy of 1 gram of coal. So, I mean, you can probably see maybe some of the benefits of using uranium compared to coal because it produces so much more heat and so much more energy. Again, the more this chain reaction is allowed to occur, the more heat and the more energy it can produce. The thing about it is it can produce a tremendous amount of energy. If this reaction is left unchecked, it could cause an explosion because there's so much energy produced, and that could be a bad thing. And we'll talk about the repercussions of that in a couple of minutes. So here is sort of the insides of a nuclear power plant. And before we kind of get into this, I want you to kind of look at the top here, where it says the primary system and the secondary system. Okay, the secondary system, I mean, we see things that are kind of familiar to us, right? We see the turbine, right? We see the generator. that would connect eventually to the electrical grid. All that electricity can come to your home. There's a condenser in here. There's water that gets pumped in. So this is very similar to a coal power plant. Now, on the left here, this is the primary system. This is where it differs a little bit because we're not using coal. We're not burning that coal to heat up the water and produce the steam. Instead, we're using uranium 235. Okay. So what we have here, this is what we call the containment structure. This is this kind of yellowish area here. The containment structure is typically several feet thick of concrete, lead, whatever it is. But it's important that containment structure is intact because remember what I said. I mean, this nuclear energy, this uranium, this chain reaction that takes place. If something goes wrong, it can produce a tremendous amount of heat and energy. And that containment structure is basically set in place in case there is a possible explosion or some radiation that possibly can leak out. But anyway, if you take a look on the inside here, you have what we call your fuel rods. Your fuel rods are basically your uranium 235. All right, and they're usually submerged, or they are submerged in water to kind of help keep them cool. Um, but those fuel rods are used again to heat water. They are there's a chain reaction that's taking place. They are producing heat, and that water is being heated up and producing that steam to spin the turbine. Now the thing is, that amount of heat has to be regulated. It can't get too hot. If it gets too hot, this whole thing is gonna blow. So to kind of help negate that, we have these structures called control rods. Now the control rods are put in place to help absorb some of this reaction, kind of help absorb some of the neutrons that are free to kind of bump in and to cause more fission. So when those control rods are lowered into the water, it actually helps slow down the chain reaction. It slows it down so less heat is produced. When those control rods are raised up, it allows the chain reaction to continue. So that means more heat's being produced, and then they'll be lowered down to slow down the process, and they're raised up to heat up the process. So those control rods are put in place to do exactly what it says they do. They are there to control this reaction. Because if it's not controlled and it's uncontrolled, then you've got a major problem here. Okay. So that is really, really important. So let's go through a couple things here. Again, we said the containment structure. All right, that's very important. That's set in place. That has to be constructed. The fuel rods, again, that's what contains the nuclear fuel. And then, of course, we have our control rods. And again, those control rods, probably one of the most important parts of the whole reactor. Because again, if those aren't put in place, if those aren't controlled, then we've got a major issue on our hands. But as long as this whole operation runs smoothly, I mean, there's a tremendous amount of heat that can be produced to again, boil that water and eventually produce the electricity. So what are some of the advantages of nuclear fuel? All right, number one, and this is a big one, no air pollution. Remember we talked about a coal power plant and all the pollutants that are given off from coal. There's no fossil fuel burning here. There's no combustion reaction. There's no carbon dioxide being given off. There's no methane gas being leaked out. I mean, this is essentially clean energy. No pollution. Again, at the point of production. There's a low cost. After it's constructed, I mean, it's not cheap to build a nuclear power plant, but after it's constructed, it's actually very cheap to run in comparison to a coal power plant. More electricity can be generated this way. It's much more efficient, compared to fossil fuels. And if we're not burning fossil fuels, then I guess that means we're less dependent on those things, which is always a good thing. So these are some, I think, some major advantages, especially number one. I mean, there's environmentally, it has the potential to be much better for the environment than, let's say, burning coal. Now, some of the disadvantages. One, uranium has to be mined for. So again, all those issues, with mining that we've talked about before, those are all brought to the forefront because again, we are mining for uranium. But that is different from mining for a fossil fuel. But still, we do have some mining issues there and the impacts on the environment. Thermal pollution. I'm going to show you a picture real quick. This is typical of what kind of what a nuclear power plant looks like. This is one, or was one, that was near a place called 3 Mile Island. We'll come back to that in a minute. But you notice like all of this white, I guess it kind of looks like smoke. It's not really smoke. This is basically water vapor. It's steam, that comes out of these smokestacks. And even though there's not any like, chemical pollution in that, it's just water vapor. It is warm, so it does create, thermal pollution of the air, and it also can produce thermal pollution in water as well. Because again, water has to be pumped into the nuclear power plant. That water is warmed up. It does have to leave the plant as well. If that water is not cooled before it goes back, let's say into a river or a stream, then it could produce thermal pollution as well. But this could be air pollution. It could be water pollution. It's just not chemical. It deals with heat, the raising of the temperature of the air or of the water. There is a high initial cost to building a nuclear power plant. They are fairly expensive to build them, but once they're built, again, they're fairly cheap to maintain and to operate. So there is a high initial cost in comparison to a coal power plant. Then finally, number four, and this is kind of the one I think that it probably is what keeps us from producing a lot more nuclear power plants in our country and around the world, is the potential for accidents. Accidents have happened. There's only been a couple major ones around the world in the last 40 or 50 years, but they do cause quite a bit of panic. When people say that they're going to build a nuclear power plant, and if that's like near your home, then like people get kind of freaked out about it. So I want to talk about three different incidents on the next couple slides. That'll kind of show you what I mean by why people might be a little bit scared. And finally, number five is just how we store the radioactive waste. There is waste that's produced, and we do have to store it, but it is radioactive material, so that has to be put somewhere, and that's not always an easy solution. All right, so a couple of notable accidents that have happened with nuclear power. The first one is 3 Mile Island in Pennsylvania. This is the closest that we've ever come in the United States to actually having a nuclear meltdown and a nuclear accident. It happened in 1979, and what happened was the reactor core overheated, mainly due to worker oversight. I don't know the exact details of what happened. You can probably do a Google search and find out. But the core, the reactor core, did overheat to the point where there was a partial meltdown. Now, the actual containment structure never broke. It didn't leak any radiation, at least supposedly, out into the town of 3 Mile Island. But there was a real fear that that might have happened. So anytime there's a reactor meltdown, and a possibility that that containment structure may break, then that means that all of the radiation produced from that chain reaction could get leaked out into the environment. So initially, what happened was 200,000 people had to evacuate their homes, and they were freaking out. I mean, this was like a national news story. This had never happened in our country before, and there was real fear that people were going to get radiation poisoning and get sick. But they found out that it was fairly well contained. there were no documented deaths or even illnesses that were caused by 3 Mile Island. But there's been some studies, some long term studies that have been done of the population of people who live near that area. And what they have found is that infant mortality rates, infant death rates, and cancer rates did slightly go up in the following years after this incident took place. Now, did they actually link it back to the meltdown? No, they didn't. I mean, maybe it was just because of chance, but there were some interesting, findings that they found, some medical studies that were done, but it never was really linked back to 3 Mile Island. This is a picture here again of the actual reactors right here in the middle, and like I guess what you don't really see here in this picture. I mean, you do see, but you have to look really closely. Is back here. Okay, right back where my cursor is, this is where a lot of people live. Okay, there's like a little town over here, and even back over here. So again, any radiation that may have leaked out of this reactor, those people are close enough to have possibly have been exposed to that. But again, this is what I kind of characterized as a near miss, right? I mean, we kind of dodged a bullet with this one. It could have been a lot worse than what it was. Now, another accident that took place was one in 1986. This took place in Chernobyl, in the Ukraine. This is the former Soviet Union. At the time, it was the Soviet Union. This was under communist control in Russia. In this case, what happened again, worker error. Cooling rods were not put back in time. And what happened was there was a complete meltdown. The core overheated to the point where this chain reaction caused an explosion, and the whole reactor core basically could not contain this explosion. So there was radiation that was leaked out into the environment, and it was a huge amount. 31 workers died immediately, like within an hour. They had so much radiation exposure, so many radiation burns that they just died. Um, Thousands of other people eventually succumbed to radiation poisoning as well, but it took them several weeks to eventually die from the radioactive material that they were exposed to. Not only that, but at the time that this occurred, the Ukraine is fairly close to the continent of Europe. So, the wind would carry a lot of that radioactive dust and radioactive debris, and it spread across Europe. 100,000 people had to be evacuated around the town of Chernobyl. Many of them did get sick, many of them did die. Since the accident, 5,000 people ended up getting thyroid cancer. A lot of them were children. Some of this was non-fatal, but there was birth defects that have been found in people who lived near the accident. The thing about this one, which makes it kind of an interesting one, is because it was under Soviet control. This was the Soviet Union back in 1986. The Soviets were very reluctant to release any information to the public. So, I mean, how many people died? How many people like really got sick? Um, it's most likely very underestimated. They said 31 workers died immediately. Thousands of people got sick, but the numbers are probably much higher than what was reported. All because of just the way the Soviet Union kind of handled their business. But this was a major disaster. I mean, this is kind of an interesting picture because this was taken, after the accident. The people that were flying the helicopters and the planes over the reactor, a lot of those people died because they were so close to the reactor, they didn't even know that they were being exposed to a tremendous amount of radiation. So even though these pictures may have survived, The people did not that were actually taking the photos. Kind of interesting. The third accident was in a place called Fukushima, Japan. This happened in 2011. This was a nuclear power plant that was built back, I want to say the 1960s is when it was built. And it was built right on the coast of Japan. It's a place called Fukushima. Well, what happened in 2011 is there was an earthquake that happened well off the coast. It didn't really happen near Fukushima, but it was a magnitude 9 earthquake. It created a tremendous tsunami, a huge tidal wave that eventually crashed into Fukushima, and the reactor shook, and it caused an explosion. And again, radioactive material leaked out of the reactor, and kind of similar to Chernobyl. There were people that died, people got sick, but a lot of the